Welcome everybody, welcome to this tutorial videos about the Concawe NO₂ source apportionment viewer. I'm Thanasis Megaritis, the Science Associate for Air Quality at Concawe, and we are gonna see some slides before getting started with the real demo of the tool about what has been the motivation behind, what is the objective, and what has been the methodology that has been used in order to prepare this tool jointly with VITO. A bit of content of my presentation today about the objective, the motivation, and the methodology of the tool. And let me start it by saying a few words about what is in status now about the Ambient Air Quality Directive, which is under revision process, actually in the very final stages at that moment. And the revised Ambient Air Quality Directive sets new and more stringent standards that should be attained by 1st January 2030. So, for example, by 2030, the annual limit values for NO2 is reduced from 40 micrograms to 20 micrograms per cubic meter, while the directive sets as a core focus the 2050 zero pollution objective, which is actually to align as close as possible with the most up-to-date WHO air quality guidelines. Recently, WHO revised their guidelines, and for NO2 annual average concentrations, we went from 40 to 10 micrograms per cubic meter, while they have also introduced a 24 limit value of 25 micrograms per cubic meter. Well, these are just numbers that need to be attained in order to speak about compliance, and then let's have a look on what does it mean in terms of compliance. And in this slide, in the figure at the left, you see the map of Europe with the different dots representing the different monitoring stations measuring NO2 all over Europe. And this is a comparison with what is the standard of today, the 40 micrograms per cubic meter. And you can see that we don't have any compliance issue with NO2 limits in Europe. So approximately 99% of the stations are measuring in 2023 concentrations below this limit. The situation changes when we consider the WHO air quality guideline, the 10 micrograms per cubic meter. In that case, you see that the picture is completely different, with a lot of reds and orange dots, meaning that we have concentrations above that limit of 10 micrograms per cubic meter. And it's a fact that in 2023 we have almost 30% of stations measuring concentrations above the air quality guidelines of 10 micrograms. That also gives a signal that we need to take measures, we need to be effective in order to improve compliance, and in order to take measures we need to understand what is the source, contribution, and what are the different sectors contributing to the NO2 concentrations, and of course to other pollutants as well. And here is just a figure to explain how important is source apportionment. And on the left, what you see is actually the sectoral contribution of NOx emissions all over the years, considering the Europe Clean Air Outlook 2 scenarios as they have been used by the Commission. So with the CLE, we refer to the current emission legislation scenario, while MTFR and MTFR plus 1.5 live scenarios correspond to the most extreme scenarios in terms of emission reductions. So it's important to understand the contribution of the source, because this is not constant over the years. In 2020, the graph shows that road transport is a significant contributor. Actually, the majority of NOx emissions in Europe comes from that sector, while over the years we see a significant reduction all over the sectors. But this is even more predominant for road transport, while we see that in 2050, under the current legislation scenario, we have almost 90% less road transport NOx emissions due to the fleet turnover. This is also reflected in the pie charts when we compare the sectoral contribution in 2020 with the sectoral contribution in 2050, and we see which sectors are the top priorities in terms of effective emission reduction measures. And with that, what I would like to emphasize is actually what is currently acknowledged, that source apportionment is a key element for the assessment of air quality over the regions and the cities, and of course over Europe, and a key element in order to decide effective air quality plans and to take the most effective mitigation measures. Typically, when we talk about source apportionment at EU-wide scale, we usually use modeling tools, chemical transport models at a core grid resolution of almost 7 to 7 kilometers. But we know that NO2 is a very spatial dependent pollutant with a very steep gradients, especially close to the canyons. And it's also reflected from a recent work that VITO had done. They had a very long-term measurement campaign in a highway close to Antwerp, where they measured NO2 concentrations in different locations close to the street. And you see with the blue dots in the graph how different is the NO2 concentration profile over the areas. Imagine that a few hundred meters away from the source, we see a significant reduction of NO2. So it's important to remember this when we try to combine these two aspects, the EU-wide scale with the traffic-related pollution and the high spatial variability that pollutants like NO2 has. So the challenge is how we combine these two methodologies, the high resolution with the low resolution, and how we move from the continental scale to the local scale and to the street canyon hotspots in order to get a better understanding of the traffic sector, mainly because this is the most dependent sector of these steep gradients, and how we get a better understanding of NO2 pollution in cities. To this end, and in order to better understand this, we joined efforts with VITO. We have developed the Concawe NO2 source apportionment viewer. It's an EU-wide, a high-resolution viewer based on a state-of-the-art methodology developed by VITO, but also in combination with other methodologies developed, in that case, from the Joint Research Center of the European Commission. Now, what is the objective behind this tool? The objective is to offer an online analysis dashboard and to assess the impact of local and EU-wide traffic measures in comparison to measures in other sectors on NO2 concentrations, and eventually to improve compliance assessment. There are a lot of functionalities. We are going to see in a few minutes what is this. And some of them, the most important is that the tool considers emission projections towards to 2050. We are aligned with the second Clean Air Outlook scenario. We have a viewer that provides information about the fleet composition per country in terms of vehicle category, fuel and Euro standard, while also the user is able to assess compliance for the entire European NO2 network. Source apportionment can be assessed at city level. We are covering almost 1,000 European cities in the viewer, and we have several functionalities in order to assess the effect of traffic measures, either at city level or EU-wide, to NO2 annual mean concentrations, and eventually to compliance. Last but not least, the tool offers a user-configured emission standard, so the user can set a new Euro standard, a Euro 7 standard for diesel and petrol passenger cars, diesel and petrol light-duty vehicles, and diesel trucks. And at the bottom of this slide, this is the link in order to access the tool. Of course, you need to apply for an account, and you can after play with the tool and get a better understanding of what we have developed. Now, as I said, what has been the main challenge is how you combine these two aspects, the long-distance transport at European scale and the high resolution in cities, considering the stroke gradients close to roads. Well, modeling the long-distance transport, usually what we have is to use chemistry transport models, but these are too slow for a viewer and an application like this, that we want to have a fast response to be user-friendly. And a solution that came up was to actually use the SERPA source receptor model, a tool that has been developed by JRC, to model the impacts of each individual sector separately inside and outside the city. While for the high resolution close to roads, typically what we use is a Gaussian dispersion model, which is again very slow for the requirements of this viewer. And in that case, VITO has come up with a similar modeling application, a meta model that is able to mimic all the physics of a Gaussian dispersion process at a very high resolution of 100 to 100, which is quite high for those purposes. I'm not gonna say in a lot of detail what is the calculation procedure steps. We have recently published an article describing the methodology in a lot of detail. I will only say here how the concept is structured in order to develop the methodology and eventually the design of the viewer. So what we have is actually, we start from the long distance low resolution impact of each of those 9 non-traffic sectors. Then what we have is the traffic inside and outside the city. We model this long distance low resolution impact of the urban and regional traffic emissions. And then regarding the high resolution impact, this is split into 42 different categories per vehicle category, per Euro norm, and per fuel for each of those. And what we do after is to combine them, taking into account all proper double counting corrections. And then what we have is the NOx translated to NO2 concentrations in the viewer, and at the end we come up with a map like this that I'm using here in the example for the city of Graz. And as I said, the methodology is explicitly mentioned and described in the paper that we recently published in a peer review article, while there is also a user guide that can be found in the tool. Now, a few more things about what are the strengths. So we talk about a fast and user-friendly interface. The user is able to assess multiple scenarios and multiple years. Also, we are considering 10 different sectors, and each of them can be assessed separately. As I said, long distance and local traffic impact is modeled, while for traffic we have the high resolution modeling, while for other sectors it's a low resolution modeling, simply because traffic is the most dependent sector considering the steep gradients. The user is able to get information for the entire European NO2 monitoring network, while, as I said, the tool also includes additional analysis at city level with almost 1,000, actually 947 European cities included in the analysis. Of course, none of the modeling applications is perfect. We cannot have an ideal model, so we need to consider that there are also limitations, there are also things that we need to consider in any interpretation of the results. And first is the traffic densities, which are not based on observations, simply because it's impossible to have real traffic data all over Europe for every individual city, for every individual region, and that's why we are taking into account some proxies in order to account for these traffic densities in the different road types. Also, what is important to highlight is the effect of street canyon. We know that street canyon has a significant effect on NO2. It's something that we cannot consider at the moment in the model, simply because we cannot have this information. We cannot model every single street canyon in Europe. However, we are taking this into account, and we try to somehow solve this by using a relative bias correction based on observation, real observations for 2018, and modeling in the same year that is applied for the traffic stations. So with that, I would like only to close this session, this slide, by saying that in order to move faster to any compliance improvement with any given standard, we need to understand better the contribution of the different sources, among other factors. We need to use models, and air quality model can offer a means of robust and evidence-based approach in supporting air quality assessment and compliance assessment. And in some cases, like pollutants like NO2, EU-wide measures may not be sufficient enough in order to improve and further achieve compliance with the given standards. And we need to understand the hotspots. We need to understand what are the peculiarities in each individual city in order to get the most effective reduction strategy per region, per city. And this is something that the Concawe NO₂ source apportionment viewer can do. It can provide detailed information about the contribution of emission sources and can eventually be used to determine the most effective solutions for improving air quality. And with that, I would like to thank you for attending.